Welcome to part 2 of information theory. In this short presentation, we consider information and how it is related to Shannon entropy. Before a coin is flipped, we are uncertain about whether it will land heads up or tails up. If the coin is fair, then we are equally surprised whether it lands heads up or tails up. But if the coin is so bent that it lands heads up 90% of the time, then a head is unsurprising and it provides only a small amount of information. In contrast, a tail is quite surprising because it occurs only 10% of the time, so it provides more information. Thus, more surprising outcomes provide more information. The average information of a flip is called the Shannon entropy of a coin. Information theory formalizes these common sense intuitions about the relationship between surprise and information. Now let's make a start on how all this works in practice. Imagine you flip a coin which lands heads up. We will use X with a subscript H to represent a head. If this is a fair coin, then the probability of a head is 1/2, represented like this. Shannon defined the amount of surprise or surprisal of this outcome as the log of 1 over the probability of this outcome. Thus, as the probability of an outcome increases, it becomes less surprising, so the information provided by this outcome decreases as shown here. Take a moment to study this graph. From the previous slide, the probability of a head is 0.5, and the amount of information we gain if the coin lands heads up is the log of 1 over the probability of a head, which is the log of 1 over 0.5, which is the log of 2, which is 1 bit, as shown in this graph. Note that all logarithms used here have a base of 2, which ensures that the unit of information is the bit. If the probability of a head is 0.5, then the probability of a tail is 1 minus the probability of a head. So the amount of information we gain when the coin lands tails up is also 1 bit. But suppose we use a coin which is so bent that it lands heads up 90% of the time. When this coin is flipped, we expect it to land heads up, so when it does so, we are less surprised than when it lands tails up. The more improbable a particular outcome is, the more surprised we are to observe it. According to Shannon, more surprising outcomes provide more information than expected outcomes. If the probability of a head is 0.9, then the amount of information we gain when the coin lands heads up is the log of 1 over the probability of a head. Which yields 0.15 bits. Given that the probability of a head is 0.9, the probability of a tail is 1 minus 0.9, which is 0.1. So the amount of information we gain when the coin lands tails up is the log of 1 over the probability of a tail, which yields 3.32 bits. Notice that this improbable outcome provides more than 1 bit of information. Now that we know how probability and information are related, we will find the average information of a fair coin and an unfair or biased coin. The reason we want to know this is because the average information of a coin flip is defined as the Shannon entropy of that coin. The average information per flip is the total information from n flips divided by n, so we begin by finding the total information obtained from n flips. If we flip a fair coin 100 times, then we expect to see 50 heads and 50 tails. Given that each head provides 1 bit and each tail provides 1 bit, we expect to have a total of 100 bits. So the average information per coin flip is 1 bit. Crucially, average information per flip is the Shannon entropy of the coin, represented with a capital H. Next, we consider the average information of the biased coin introduced above, where the probability of a head is 0.9. If we flip this coin 100 times, then we expect to see 90 heads and 10 tails. Given that each head provides 0.15 bits and that we expect to see 90 heads, the head outcomes provide a total of 90 times 0.15, which comes to 13.5 bits. Similarly, we expect to see 10 tails, where each tail provides 3.32 bits, so the tail outcomes provide a total of 10 times 3.32, which comes to 33.2 bits. So the total information expected from 100 flips comes to 46.7 bits. Therefore, the average information per flip is the total information divided by 100. And if we move the 100 inside the brackets, then we obtain this. But we know that 90 over 100 is the probability of a head, and 10 over 100 is the probability of a tail, so the average information per flip is given by this equation, which is the Shannon entropy of the coin. We can use this equation to quantify the Shannon entropy of any coin. When we substitute the values from the biased coin in this equation, we find that its Shannon entropy is 0.467 bits. For comparison, when we substitute values from the fair coin in this equation, we find that its Shannon entropy is 1 bit. We can express this equation in the classic form derived by Shannon as follows. If we define x1 as xh and x2 as xt, then the entropy can be written like this, which can be written using the summation notation to obtain this classic equation for Shannon entropy. More generally, if there are m possible outcomes rather than just 2, then the Shannon entropy of these outcomes is their average entropy. Just in case you have not recognized it, this is the equation you first saw at the beginning of part 1, but this time you should have some idea of what it means and why it is so important. Suppose we want to transmit the image labelled as A over a satellite link. Because there are 256 shades of grey or colours here, it looks as if we need a binary number of 8 binary digits per pixel. This is because we need 8 binary digits to represent 256 colours, just as we needed 3 binary digits to represent 8 roots in part 1. But nearby pixels have similar colours as shown in B and C, so the amount of surprise or information implicit in the image is less than you might suppose. Suppose we represent this image in terms of the differences between adjacent pixels in each row, which yields this new image of pixel difference values. This has only 128 colours, which can be represented with 7 binary digits, so we need only 7 binary digits per pixel. More importantly, the process of making the difference image does not destroy any information about the original image, which can therefore be reconstructed from this difference image. This simple demonstration provides a saving of only about 1/8, but the image compression methods used in commercial systems like Netflix provide much larger savings. In fact, it can be shown that the average information of each pixel is only about 4 bits. Because we can represent each bit with 1 binary digit, this means that the original image, which seemed to need 8 binary digits per pixel, can be transmitted with only 4 binary digits per pixel. There's quite a lot to absorb here, and the full details of this demonstration are described in a freely available book chapter as described next. This example was taken from Chapter 1 of Information Theory, a tutorial introduction. Chapter 1 of this book, plus computer code, can be downloaded from the book's website listed below. The book is available from Amazon as a hardback, paperback, and as an e-book.